6.2 Instantaneous Rates of Change. Now, this paragraph here does a great job of explaining what it's all about and the purpose. So often calculating the average rate of change does not provide enough accuracy. For example, police do not calculate the average rate a car travels from Wodonga to Melbourne to determine whether or not a driver should be issued with a fine. Instead, police need to know the speed the car is travelling at a particular point in time. That is, the police need to calculate the instantaneous rate of change, not the average rate of change. Let's now take a look at this idea of a tangent line. So here I have a curve, and a tangent line is a line that touches a curve at a particular point. Let's consider the point P. And it's evenly spaced either side, so the curve moves away from that line that you place equally either side of the point. That there is a perfectly placed tangent line. So obviously you could draw any line that touches that point P, but you could draw that like so, or you could draw it this way. But what you want to do is place that line so that as the curve moves away from the line, it's even on either side. That's a perfectly placed tangent line. Now the instantaneous rate for this curve is the slope of the curve. And as you can see, that's always changing, right, because it's a curve. So the instantaneous rate is equal to the slope of the curve. What we can see here is that the gradient of the tangent line is going to equal the gradient of the slope at that point P. So what we can do to calculate the instantaneous rate of the curve at a particular point P is place a tangent line on that curve and then calculate the gradient of the tangent line. And that's what we're saying here. So the instantaneous rate of change can be found from a curve graph by firstly drawing a tangent line to the curve at a particular point that you're interested in, and then use that tangent line and calculate its gradient. And therefore what we can say is that the instantaneous rate of change at point P will equal the gradient of the tangent line at point P. Alright, so problem 1, consider the graph below and calculate firstly the average rate of change, where we've got the length varying between 5 and 20 meters. And then secondly, we want the instantaneous rate of change when the length is exactly equal to 10 meters. So let's first of all work out with the average rate of change, so between the 5 and 20 meter marks. So using my graph, I go up and onto the curve and I've got the position 5, 10. And on the curve again, I've got the position 20, 4. So my average rate of change is going to equal the gradient of the chord that joins those 2 points together. My calculation for this is going to be the change in weight over the change in length. So it's 4 take 10 over 20 take 5 to give me a rate of change of -6 on 15. Obviously that could be simplified, kilograms per metre. B, the instantaneous rate of change. So we're looking at exactly where the length is equal to 10 meters. So my technique should be to go up to the graph, place a perfectly placed tangent line, and that's already been done for us. Then look at that tangent line and locate 2 known points and calculate the gradient. So the 2 known points here are 5, 8 and 15, 4. So my calculation is going to be 4 take 8 over 15 take 5 to give me -2/5 kilograms per metre. Problem 2. Over a period of 6 hours, the temperature of a room is described by this function here. Okay, so we've got temperature of H, where H is in hours, and we've got that quadratic. It's an upright quadratic, where T is the temperature and H is measured in hours. what's the initial temperature of the room? So when we're talking about the initial temperature, we're talking about where H is equal to 0, so at the very beginning. So think about this. Here's the function. If I substituted H equaling 0 into that, then obviously that term would go, this term would go, and I'd get 22 degrees. So you could see here, it would be 22 degrees. What I'm going to do now is define the function because I'm going to do some work with the function on my CAS. So we're now going to define that function. So if I go menu, algebra, menu actions and define, and we'll put the function in. Notice here that I'm referring to it in terms of x, and I've got my temperature of x there. It's now defined. And to look at the initial temperature, so we're interested in where H is equal to 0, I can just go T of 0, and we get that 22 degrees as we'd expect. Let's also generate the graph of this just so we can see what's going on there. And so let's have it of T of X, and notice I use the variable X and I don't use H. And of course my window dimensions aren't right here, but if I change those, go from -2, and I'm interested in between 1 and 5 hours, so I might go up to 6 hours. I know that my initial temperature was 22 degrees, so I'm safe to begin at 0 degrees, and I might go up to 45 degrees in temperature. All right, so there's my graph there, all shown. Of course, I'm not going to be dealing with all of it. So obviously, time starts at 0 here, so it's 0, 22, and I'm going up, and I'm interested in something like 5 hours there. All right, so that's what my graph looks like. B, what is the average rate of change between the 1 and 5 hour mark? So I've also got a graph here showing the same information. So between the 1 and 5 hour marks, what's the average rate of change? So what I need to do is go to my curve at the 1 hour mark. There's my scale there, guys. So at the 1 hour mark, and that is the position 119, and the 5 hour mark, and that's the position 5,27. So the average rate of change is going to equal the gradient of the chord that joins the two. So it's going to be 27 take away 19 over 5 take away 1. So on my CAS calculator, then it's going to be looking like this. Bring up the fractional template. I want the change in temperature, so that's going to be T of 5 minus T of 1. So that's the change in temperature between the 5 and 1 hour marks over the change in time, which is 5 take away 1. And I get a rate of change of 2 degrees per hour. So what does my calculation look like? Sorry, back this way. Average rate of change. So as I said to you before, it'll be 27 take away 19 over 5 take away 1, or as I've done on my CAS calculator, to achieve a rate of change of 2 degrees Celsius for every hour that goes by. These are the steps of what I did on my CAS. For part C, we need to work out the instantaneous rate of change. So again, looking at my graph here, my CAS calculator is not going to be helpful at all. I'm interested for where that occurs at the 3 hour mark. So I go up to the 3 hour mark. Here's the point here that I'm concerned about. I now attempt to place a perfect tangent line at that point. So I want it to touch the curve, and I want it to be evenly spaced either side of that curve. So you can see there that I've placed this line in such a way that as I move along, the space here is about the same as the space there. All right, now I need to locate 2 points that are on that tangent line, and so I've identified 0, 12 and 6, 26. So what I can do now is say that the gradient of this tangent line will equal the instantaneous rate of change at the 3-hour mark for this curve. So it's going to be 26 take 12 over 6 take 0 to give me 7/3 of a degree per hour that goes by. That is my instantaneous rate of change. So that's telling me that as 1 hour passes, the temperature will increase by 7 on 3 degrees Celsius at exactly the 3-hour mark. Of course, this is a variable rate of change, but you can see because it's a curve, but particularly at the 3-hour mark, that is the rate at which the temperature is increasing. Here's a lot of CAS steps. Look, they're in the notes. To be honest with you guys, I don't think it's that handy at all. So I wouldn't invest too much time looking at this. It's about placing tangent lines and making them move around. I suggest you give that a miss. Okay, problem 3. The ideas here are quite complicated, and don't stress. I'm going to do lots of examples of this in class, but I'm going to cut straight to the chase and explain the theory to you rather than just approach the question. Okay, I've got a curve y equaling 3x squared, and that's traced out here in blue. I'm interested in the instantaneous rate of change at x equaling 4. All right, so what is the slope of this blue curve at x equaling 4? So what I can do is place a tangent line, and I've shown that in green here, and then calculate the gradient of the tangent line. The gradient of that tangent line will equal the slope of the blue curve, which will give me the instantaneous rate of change when x is equal to 4. I now want you to think of this idea. Let's consider a second point on the curve, which is close by. It's h units along the x-axis further to the right. So I'm interested in x equaling 4. Another point is going to be 4 plus h. So it's h units across. If I now consider the line that joins those 2 points, can you see it's a really rough approximation for the green line? So I'm saying that that black line and this green line have approximately the same gradient. I can easily calculate the gradient of this black line. So therefore I have a rough approximation for the gradient of the green line, and I therefore have a rough approximation of the instantaneous rate of change for x equaling 4. The idea here is that this second point needs to be fairly close to the first point. I'm interested in the instantaneous rate of change when x is equal to 4, so I'm going to make use of a point which is nearby, which is x equaling 4 plus h, and then obviously the substitution of 4 plus h into this rule here to give me the corresponding y value. Now, if we brought this second point even closer to the first point, you can visualize the line that would join where I am at the moment to x equaling 4 there, and you can see that that is even a better approximation. And then if I even reduce that distance between the 2 points, you can see where exactly I am now on the cursor, and you can visualize again a line that would join the 2 points. Then you can imagine that the gradient of that line would be extremely close to the gradient of the tangent line, and therefore the gradient of that smaller line that I just described before would be a very close approximation for the instantaneous rate of change at x equaling 4 for the function y equaling 3x squared. And that's the whole idea behind it. Notice that the distance between the 2 points I'm referring to as h. It's that horizontal distance. So hopefully now this will make sense to us. We've got a function y equaling 3x squared. We need to work out approximations for the instantaneous rate of change in y with respect to x for x equaling 4. So, hey, what's the instantaneous rate of change here at this particular point? And what we're going to be using is values of h, which are 0.1 apart, then 0.01, then 0.001. Now, if these points are known, then to calculate the gradient of the secant that joins those two is quite easy. It's going to be the change in y over the change in x. First of all, let's consider where this point is. So when x is equal to 4, what's y going to equal? So x is equal to 4. We now substitute x equaling 4 into the y function to get 48. So I know that this position is 4, 48. Let's now consider h equaling 0.1. So this is initially 4. If I go h units across, and I've described h as being 0.1, this new position over here is going to be 4.1. This point is going to be the substitution of 4.1 into this rule. And I've done that calculation. So for where h is equal to 0.1, then I'm going to have x here being 4.1. If I substitute 4.1 into the function, I'm going to get 50.43. So now what I know is that this point is 4.1, 50.43. And this point here is going to be 4, 48. So to work out the gradient here of that line, it's going to be 50.43 minus 48 over 4.1 minus 4. So change in y over change of x, and I'll get an estimation for the gradient. And I've shown that calculation here. So for where h is equal to 0.1, then I'm going to get what I just spoke about to get the approximate gradient equaling 24.3. So what have I just achieved? I've said that the gradient of this black line will be approximately equal to the gradient of this green line. So therefore, the gradient of that black line is approximately equal to the instantaneous rate of change for where x is equal to 4. And I've just done that calculation to show that the instantaneous rate of change for x equaling 4 using a value of h equaling 0.1 will give me 24.3. Let's now get a better approximation. So let's bring this point a bit closer in. And let's now make that horizontal distance between the 2 points, the value of h, equaling 0.01. So now h equals 0.01. So there's 4. I'm going to be moving across to having x equaling 4.01. Subbing 4.01 into the function, I'll get 48.2403. I can now do a calculation for the gradient, and you can see that I'll get the gradient equaling 24.03. So if I use h equaling 0.01, then the gradient of the black line is equal to 24.03. So therefore, what I can say is that the approximation for the instantaneous rate of change is going to equal 24.03. Again, I can be more accurate. And now let's make the horizontal distance between the 2 points equal to 0.001. So it's almost on top of it. And you can see that my change in y over change in x produces a gradient of 24.003. So I can say that the approximation for the instantaneous rate of change using the technique that I've described where the horizontal distance between the 2 points is 0.001 gives me 24.003. So what we're seeing here, guys, is that as the horizontal distance becomes smaller and smaller, so as h approaches 0, the gradient is getting closer and closer to 24. And I write that like so. What I've just said here is the absolute fundamentals of calculus. It's what we call first principles. And we'll be playing around a lot with this in the future. I understand that this particular problem is extremely heavy for you at this stage. But if you can pick up anything from that, that's fantastic. To be honest with you, it's probably almost too difficult to place in the notes at this stage. Well done.